Any questions before we got about a minute? Any questions before? I didn't get started. Remember, there's an exam in class on Wednesday. It's just going to be devoted to taking the test. It's not going to be, I don't think it'll take most of you the full time, but there is a practice test on Canvas, and it's going to be very similar to that. So you can do the practice test, and within 50 minutes, you'll be in good shape. Yes, sir.
For that homework, can you explain number 4, like kind of what you were looking for the explanation part?
Yeah, I'm going to go through that today. You're talking about today's homework, right?
Yes.
Yeah, I'm going to do that today. Okay, so we're looking at a particular wave equation. Actually, I was incorrect. It's not a wave equation for deep water, but it is the wave equation that you get from electromagnetism, from Maxwell's equations. It's also the wave equation that you have for a thin wire under tension, like a string under tension. I'm going to talk later about different kinds of wave equations that you get. We're just going to look at the one at the beginning of class today, the one that was in the homework, which has the second derivative in time and the second derivative in x. And so we're going to talk about that. But then after we get past this discussion, I'm going to show you some other examples of wave equations. And it's related to the question of what's called the dispersion relation. This wave equation that was in the homework today has a particular relationship between the frequency and the wave number. And that general relationship for wave equations generally is called dispersion relation. And I'll give you an understanding of why it's called dispersion when we get to the more general case. Okay, so for this particular wave equation, I'm sorry, there we go. For this particular equation, there's a particular relationship between the frequency and the wave number, which is that the frequency is proportional to the wave number, and the proportionality is the speed of propagation. So it's a very simple wave equation. And what as I demonstrated in class last time, that just means that the wave, whatever the shape of the wave, it will propagate intact. So whatever the shape of the packet, whether it be oscillatory or localized, doesn't matter. It's just going to propagate intact in one direction, to the left or to the right. Okay, so here's let's see, just to help your visualization, this is cosine. I'm going to set k and omega to 1. So this is cosine minus xt. And so I'm plotting it versus x, and then I'm animating it in time. So you can just see how the solution propagates to the right. And you can see that the propagation ought to be to the right here, because if I pick a maximum, a local maximum, that occurs, for example, where the cosine might have argument 0. For example, that would be one of the maxima. So x minus t is equal to 0, so x is just proportional to time. So it should just slide to the right. And if we flip the sign here, then I would do the opposite. So let me stop this and just flip the sign, SIGN of the argument of the cosine. So now I'm plotting cosine of x plus t. And I'm just going to animate that, and it will travel to the left. Okay. So it is kind of challenging to plot functions of multiple dimensions. And so one way is to imagine doing this, take snapshots at different times. And then you would see, for example, at slightly different times that this thing moves sliding to the left. Okay, so you might take 2 snapshots at just slightly different times, showing that the cosine is sliding to the left for this particular image. I'm going to show you, if we take a superposition of right traveling and left traveling waves. So take a cosine x minus omega t plus cosine of x plus, x minus t plus cosine of x plus t. And I'm going to make the amplitude be half. Okay, now you can use the trig relations for the sum of 2 angles. Sum and difference of 2 angles. Simplify this, and this becomes cosine of x times the cosine of t. The sine terms cancel out. This is a standing wave, so I can take a superposition of a right traveling and a left traveling wave, but they have the same strength, 1/2 here, both of them. And this is the result in a standing wave. Looks like this. So this is not traveling, but it is oscillatory in time. It's not traveling to the right or to the left. And so notice here that there is a brief instant where the wave has nulled out everywhere. But it's got velocity in the sense that it's going to be moving up or down. So the nodes, there are places here that occur where the nodes in X, where the wave is always 0, and that would, you could see here cosine of X, where cosine of X is 0, then it's going to be 0 for all times. So in other words, for X is pi over 2, excuse me, pi over 2, 3 pi over 2, 5 pi over 2. So those are those nodes, and those are always 0. So we're going to see when we're studying Schrodinger equation, we're going to see some solutions that are traveling wave, and we're also going to see standing wave solutions. This is a general property of wave equations that you can superimpose things to get either, you can superimpose traveling waves to get standing waves. Okay. So I hope that helps you to visualize these solutions a little bit. Wait, okay. All right, I'd like your help, by the way. Oh, let's see, I'd like your help. You're supposed to mute the. Oh, it's on. Oh, I want to turn the power off. There we go. Okay, good. I want your help, please. Remind me, this camera that's recording the Zoom, just up there, is only getting to about here. And when I go over there, I'm going off camera. And this is going to mess things up if you're trying to watch the Zoom recording. And of course, so I don't want it to be incomplete. So I'm trying to remind myself by drawing lines and staying inside the playing field here and not go out of bounds. So I'll need to remember that next time. I've got these marked now. I'll remember today, but Friday I won't probably. So I'll be out of bounds again. Okay, so some general terminology about things. A function can be thought of as a map from numbers to numbers. So a function is like a machine that takes an input and then spits something out. So it could be takes a number and spits out another number. And we generalize this to cover complex numbers. So the input could be a complex number, the output could be a complex number. So we could talk about functions mapping a complex number in general to a complex number. Example of a function is just x squared. Just multiply the number by itself. If it's a complex number, it's the square of that complex number. So it's also, again, a complex number. So in general, complex functions or complex numbers are themselves complex numbers, right? That makes sense. All right. We also have something called a functional. You know what this is. You don't perhaps know the terminology, and you're going to see more functionals in later classes in physics, but I wanted to mention it as a kind of contrast to a function. So a functional takes a function as an input and produces a number. You think of an example of a functional. An integral, a definite interval, the area under the curve. So let's say the area under some bounds, this is a number. If the function is a complex number, then this is a complex number. So functional takes a function, maps it to a number. If the function is itself a complex function, then the number it produces will be in general complex. So thinking of this as an area, if this is a real function, but then you could generalize this to be a complex function here of a real number, for example. So that's an example. Lots of examples when you start thinking about what you've been dealing with before. In this class, we're going to spend a lot of time talking about operators. An operator takes a function and produces another function. So if I have a function, goes in, an operator spits out another function. Can somebody think of an example of an operator? A derivative. So think of this. The derivative of a function produces another function, which we call f prime. F prime is just another function. So the derivative of x squared is a different function, it's 2x. So I take any function as an input, then I produce another function. The derivative produces a particular function. Yes.
Would the wave equation be an operator?
Yeah, that's where I'm going with this. The wave equation is an operator on some function is equal to 0. All right. Good for you. How about some other than derivative? Just multiplying by a constant is an operator, a trivial operator. 2 times f of x is just 2f of x, right? So 2 times x squared is 2x squared. That's trivial. Multiplying by a constant. Multiplying by another function. So I have what's called operators are often designated with a hat on top, which is a little confusing if you're used to using hats for unit vectors. They're not unit vectors. And sometimes you may run into a situation where you might want to use both at the same time, so you got to keep your wits about you don't get confused because you're using the same symbol to mean 2 different things, and that can be trouble. Okay. But it's common to use a hat. So you could define a function, an operator called W, which is to multiply f of x by some particular function W of x, potentially. That's an operator. Trivial operator. You just multiply by constant or multiply by a function. Derivatives is a little bit more. It's the slope of the tangent at a curve. Another one is the indefinite interval. Okay, so this you could say is let's say let's call I acting on f of x is the integral of f of x, the antiderivative of f of x. So we could say this is the derivative is and the integral operators, the antiderivatives are inverse operators. So I could have a operator equation, right? First differentiate, then I integrate. Right, and so I could have, let's call d of x, the hat over it, that's the derivative operator. I could have something like this. First and it reads from right to left. So I have the function. It's going to be operated on first by I, and then the result of that's going to be operated on by D. And any function is going to be returned by this successive operation. First integrate, then differentiate. Okay. So I can have operator equations. The wave equation is an example of an operator equation. Based on derivatives, the equation that you've studied is an example. But let's notice a particular property of the derivative operator. So with D, I can write this. This is an expression about the operator itself. The understanding is that you're going to operate on some function. So this doesn't really mean anything until I recognize that this is going to be operating on some function. Okay? But I could have an operator and the integral operator, this say that this is 1, which means this. Because it's true for any function, I can write it in an abstract form as applying to just the operators themselves, even though the understanding is that you're always going to be applying this to a function. All right, so let's look at the wave equation. Let's see, I could have this operator, I'm going to use a subscript x. This operator, I'm going to use a subscript. I'm going to make these partial derivatives because they're going to be acting on functions of 2 variables, x and t. Okay, so the second derivative then is a square of this operator. And the second derivative here let's just say h of x is t is equal to 0. And this thing is called the del inversion, also called the square bracket. So this is another operator notation, square bracket on a solution of the wave equation always gets 0. Away from where the source is acting. We have to modify this equation to include how the action of the source, but we're looking at the solution away from the source. We're just saying that the source is doing something, and we're going to study what happens away from the source. So this is the wave equation written in compact form. Okay, now these operators have these particular operators that I've been showing. Multiplying by a constant, multiplying by a function, derivative, any number of derivatives, integrals, antiderivatives, any number of those are all linear functions. A linear operator, excuse me. A linear operator property if it operates on the sum, that is the same as the sum of operating on each one. Which also has the property that a constant passes through the derivative operator. So if I multiply by 2, operate on that, it's the same thing as operating on the original function and multiplying by 2 after. Okay, so is the derivative a linear operator?
Yes.
No. By definition. You can remember the definition of this. We hold t fixed. Displace x, take the difference. And so we can see if this is, if f is the sum of 2 functions, f is equal to g plus h, then I get up here the sum. So let's try to do that. So I get g of x plus epsilon t minus h. And then I subtract off the sum at x. Okay, and then I just regroup the terms. I just divide them separately here. So I have 2 separate terms here. G of x plus epsilon plus the same limit for h. So this is equal to g prime plus h. Okay. Then a second derivative by the same principle, the second derivative is the derivative acting twice. Right. So the second derivative is also a linear operator. Oh, I'm sorry, can I erase everybody okay? That's the problem with running out of space, is I got to start erasing faster. And Dr. Padilla showed, no, it was somebody, Dr. He showed me this film in Bali, which was about engineering students. And the professor was writing and erasing like this. very talented. He could do that. Impossible to take notes, of course. But anyway. So if A is a linear operator, then A squared is linear. Right? Because A squared is just apply A and then apply A again. And the first application is linear, and the second one will be linear. They get the idea. Okay, so that means the del inversion is linear. See how to demonstrate that? Basically the idea. So this is linear, which means that any solution to the wave equation, any two solutions to the wave equation, I can create other solutions to the wave equation by adding them, subtracting them, multiplying by constant coefficients. Right, so if I have two solutions, E and H, then another solution can be written as a linear superposition. Any of these are constants. And for this, the del inversion acting on this is also 0. So that's how I, for example, could take a right traveling wave and a left traveling wave, add them together and get a solution, which was now a standing wave. Different character. Yes, ma'am.
This might be a really dumb question, but what is the square?
The square is just this.
It's just the wave equation.
Yeah, it's the operator for the wave equation. So it might be more commonly written like this. This is the square. It's the operator.
So it's just everything that's in those brackets.
Yeah.
Okay, cool.
It's called the del inversion. Del inversion. So it's an operator which has two derivatives in x and t. And that's a very succinct way of writing our wave equation. Del inversion on something is equal to 0. So the del inversion, this is a particular wave equation. I keep wanting to remind you of that fact that we're studying some particular solutions of a particular wave equation here. So I'm going to show you some changes, some differences, what happens if you do something else. So this will apply to the very thin wire or to electromagnetic waves. Those will all satisfy the del inversion electromagnetic waves in vacuum, in the plot, without air, without not traveling through glass or something else. Yes, sir.
If it is talking about like all like the Plana waves are all, that's all, the C is the speed of light, right?
Yes, sir. Right. So in electromagnetism, so there are lots of waves in the plot. Gravitational waves, electromagnetic waves, there are other waves too. But for electromagnetic waves, there's just the speed of light. Actually, for gravitational waves, it's a similar equation with, again, the speed of light. It's a kind of a maximum speed of propagation, which we happen to know is light is traveling at that speed, but it's not the only thing that travels at that speed. Yes, sir.
And when we did the solution, like in the homework where it was omega or k equals omega over c,
Yeah.
What is that telling us?
Yeah, that's the dispersion relation. So I'm going to talk about that coming up right now. Okay. So a particular kind of solution to this equation is called a plane wave. Complex could also be written as cosine. So cosine kx omega t. If I flip the sign, I also get a solution. Sine kx minus t is also a solution. If I flip the sign here, it's also a solution. Cosine and sine are independent solutions. To get a full description of a wave, you need both of them because they're shifted out of phase with each other. So to get a complete description, you need both components. And from the Euler relation, you can see that both of the components are very compactly written in this complex exponential, because this has both cosine and sine as the real and imaginary parts. All right, so I can say that this is equal to 0. This is a compact way of saying both of those restrictions. Okay, now if I substitute that into this equation, oh, this is called, by the way, called plane wave. And it's not real obvious since we're not looking at x and z, I'm sorry, y and z, the other two directions, why we're calling it a plane wave. But we can imagine if we have like traveling an electromagnetic wave far away from the source, that the wave has what's called a wave front, where all of the E field or the A field is in phase. And so it's independent of y and z. So it depends only on x. And so a three-dimensional wave solution would have no y or z dependence. And so then the wave front is traveling as a plane through the medium, through the quantum. That's why it's called a plane wave. Not obvious when you're doing just one spatial dimension why you would call it a plane wave. But the reason is because when you extend it to 3 dimensions, then you have solutions like this, which don't depend on y and z. Okay, so this is going to be called a plane wave, even though we're talking about one spatial dimension. We'll still call it a plane wave. If I substitute this into here, and when I get the two derivatives in x, I get negative k squared, and that's because I get ik squared, right? That gives me a negative k squared. And then I get a plus omega squared, that's because I get a negative I omega squared. With a negative sign, you got to keep track of all your negative signs. Okay, so for this to be 0 for all x and t, and this x complex exponential is not generally 0 anyway, then what's in the brackets here must vanish. And so this gives you this dispersion relation. Okay, and the reason we're generally going to pick omega positive always, but k can be positive or negative. This is the way we're going to get left and right traveling waves. Rather than flipping this sign, we could flip the other sign, the sign of k. And so if k is negative, then it'll travel to the left. If k is positive, it'll travel to the right. So this is given a funny name. At this point, it's funny. It's called the dispersion relation. But we just have worked through the solutions. I have demonstrated to you that wave packets don't change shape if they're governed by this wave equation, this particular wave equation. Any sort of wave packet, remember it was just any function, like x minus dc, that could be anything. And this thing just slides to the right, unchanged in the shape. So it could be a localized wave packet. And at a later time, it's just going to have shifted everything to the right by a distance ct. Okay, so this is called dispersionless propagation. So there's no dispersion. This particular wave equation doesn't mean that it means this particular relationship between frequency and wavelength. Funny terminology. This wave equation has no dispersion. This equation is no dispersion. That means there's a linear relationship that we wrote down between frequency and wavelength. Okay, so what could happen? So this is what will happen: electromagnetic waves traveling through the plana. It also is a very thin piano wire. Stretch, pluck it, get some wave traveling, and so you get no dispersion in a system like that. Okay, so but other things can happen, and usually what happens, instead of writing the wave equations, very often you'll see some kind of relationship between the frequency and the wave number. And instead of writing the wave equation, they'll write this relationship, which comes from the wave equation. So here's a for instance. Let's suppose that the wire has some thickness to it. So rather than being a really thin wire, we have a thick rod, and we're looking at sound traveling down a thick rod. Then you get an equation that looks like this. There's some constant here. Let's see, it's yeah, I don't know, some constant. I forget exactly the constant. Let's write it this way. Write it in the same form as this. So instead of the delineation, you've got an additional term, which is the fourth derivative. And this constant alpha has something to do with the thickness of the rod. The details are not important. What happens here now, if I substitute a plane wave, it's still going to be a solution. If I substitute that in here now, I get k squared plus alpha k to the fourth, alpha some constant, is equal to omega squared. Like this. And now I don't have that simple relationship that omega is just proportional to k. Something more complicated. So I'll have a different kind of behavior, a wave propagating through a thick rod down the length of a thick rod as compared to a thin wire. And what will happen now is I get dispersion. Dispersion means that I can give it a kick on one end. The packet travels down the rod, but it's changing shape as it travels, spreading out or changing shape in some way.
It's for vibrations in a rod.
Yeah, this would be, for example, vibrations in a thick rod, along the length of a thick rod. Okay, so now I get some packet, which at a later time will have some other shape to it. Starts off like this, propagates along, and is changing shape as it goes. So this is what's called dispersion. It's the same thing that happens now if I consider the propagation of light through glass. The original equation has to be modified because the speed is not the same for all colors. Different colors propagate at different speeds. And so I don't have this relationship anymore. It's a modified relationship. So that happens, for example, when you pass light through a prism, it disperses the colors so that white light gets broken up into different colors. That's because the light traveling through the prism is traveling at different speeds, to different colors, traveling at different speeds. And they end up getting dispersed in the prism. That's the origin of the term dispersion. In terms of the wave equation, the dispersion relation is generally a relationship between omega and k. And this is a little bit backwards because remember, what sets the frequency is the source, right? So really, as a practical matter, you might think that you would want to know the wavelength as a function of omega if you want the inverse function. But for some reason, nobody plots it that way. I don't know why. Everybody does it this way. You would think you would want the wavelength associated with the frequency because the source sets the frequency. So you would think you would want that. But nobody plots it this way. Okay, so those are a couple of examples of thick rod, light traveling through glass rather than through just the plana. Get different dispersion relations. Okay? And so each dispersion relation means that there is a wave equation associated with that, which will be related to that dispersion. So if it's simple like this, you can almost figure out how the wave equation must be formed in order to give this dispersion relation. Right? This k to the fourth here comes from that. So you can often just pick out, you know, the dispersion relation. Analytically, you could figure out the wave equation that goes. Okay. Questions? So here's an important point. Remember, we said the Dell inversion is a linear operator. And we have this relationship between omega and k. So I'm going to here put that down, that omega is a function of k. it's C times K. Okay, it's a linear operator, and so I can superimpose, make superpositions of plane waves. So let's take this at one value of K. Let's do it this way. I can add solutions with different wave numbers. Also different frequencies. This will be a solution. I can multiply each one by a different strength. This is also a solution. And I'm not restricted to just two. I can add 3, 4, 5, an infinite number of solutions. Will still be a solution. And so I can write down for the wave equation that we're considering, and actually other wave equations. I'm going to integrate over a lot of values of K. And for each value of K, there's a strength, A of K. It's the constant out in front of that term. An integral is a sum. And I'm going to sum over all possible values of K. So I've got a lot of, in this case, right traveling waves. If, in fact, if I let K go negative here, then I have left traveling waves as well. And there's the strength of each value of K. And so this is a superposition. And so I can superimpose all of these waves and get another solution to the wave equation. So this, in fact, is a general solution to this wave equation. And it's also going to be a general solution to other wave equations, as long as they satisfy the right dispersion relation. That is, as long as omega is the right relationship to K. Well, how do you prove that? Well, you take the D'Alembert and you act on this thing. Remember, the integral is a sum. So the derivative, the D'Alembert acting on the derivative, is going to just distribute over the sum. D'Alembert acting on F. These are not functions of X or T. So the D'Alembert acts on each of the terms of the sum. And this we know is a solution to the gives 0 as long as omega has the right relationship to K. As long as it satisfies the dispersion relation for that wave equation. So this is equal to 0. So the whole thing is equal to 0. So this is a solution formed by superimposing a bunch of plane waves. It all works because of the linear nature of the wave equation and the median. So that means if I take, again, just physically what it corresponds to, if I take a wave coming this way, a wave coming this way, they just pass through each other. There's no interference between the, I shouldn't say it that way. What I mean is that they just superimpose in the way that we indicate. Okay? There's nothing more than a superposition going on. Okay, so let's see. We could have applied, instead of the D'Alembert, if we had applied the wave equation for the thick rod, we'd have the same thing. This would still be a solution as long as omega was the proper function of K here. So this gives 0. So this is going to work in general for wave equations, as long as they're linear wave equations. Do a superposition like this and construct a very general solution to the wave equation. Yes?
So aren't you adding all the way from negative infinity to infinity?
Yeah, so remember, if I fix omega as being positive here, then the speed is omega over K. If K is positive, it travels to the right. If K is negative, it travels to the left.
Yes, sir. Okay.
That makes sense?
Yes, sir.
So I can combine left and right traveling waves by allowing K to go have a negative value. So from negative infinity to zero are left traveling waves. From from zero to positive infinity are right traveling waves.
So it's just adding up all the possible
Right and left travel.
right left traveling waves that could be a superposition right there.
Yeah. K less than zero. So omega is greater than zero. You choose that. K less than zero is left traveling. And greater than zero is right traveling. So this combines left and right traveling waves. So you got everything possible really with this. Anybody familiar with Fourier transforms? Seen those yet? This is getting us into Fourier transforms. So if you know something about Fourier transforms, this should start to feel familiar. Okay, so I'm going to preview. You have a test on Wednesday, and then you have some homework for Friday. You're going to start reading chapter 2. Now, all this preparation, chapter 2. Chapter 2 has the meat in terms of the specific stuff going on for an electron and a hydrogen atom, for example. We're going to finally start dealing with this. So we're going to be developing the Schrodinger wave equation, which is sort of like the wave equation you've been studying, except it has a different dispersion relation. So remember, light has this particular dispersion relation. And remember, we have this constant in quantum mechanics. We have this constant h bar, which is Planck's constant divided by 2 pi, right? There's 2 pi's floating around here. K is 2 pi over lambda. Omega is 2 pi nu. And these constants, 2 pi floating around. So it's frequently we absorb a 2 pi here because h bar is h over 2 pi of omega. And omega is 2 pi nu. So h nu, which you saw in the Planck experiment, photoelectric experiment, and also the analysis of black body radiation, this is the energy associated with the transfer of energy from the light to the electron and the photoelectric effect, and also the black body spectrum. So if I take that equation and multiply by h bar and work out factors of 2 pi, it's the same as h nu, it's the same as E. I have E on the left-hand side. I also multiply K by h bar, multiply the right-hand side. What is this? This is h over 2 pi, 2 pi over lambda, this is h over lambda. What's the significance of that to de Broglie? What's the de Broglie relation?
That's my middle, right?
Yeah. Is h over lambda. So in this groping around that they're doing, Broglie, Heisenberg, Schrodinger, all these Einstein are doing is these relations keep coming out somehow. They don't quite understand exactly what they mean. But notice that for light then, this relationship, if we take the dispersion relation for light, we multiply by Planck's constant, we come up with this. And this should be familiar from electromagnetism. This popped up when we had an antenna over here that's sending an electromagnetic wave out this way. And then we have over here a damped harmonic oscillator with a charged body. The electromagnetic wave is coming and causing this thing to oscillate. And we found in last semester, and if you haven't covered this, I'll tell you what the result is. The result is a push on this charged body, which is hooked to a spring and has damping. It's going to oscillate. Remember, an antenna here that's sending out a signal. The receiver is going to start oscillating. Remember, there's the time delay. Start oscillating, and there's going to be a push outward, always outward. This is called electromagnetic radiation. Okay, and the energy that the radiation can deliver and the momentum that can be delivered is related by this. This comes from Maxwell's equation, this relationship. Going through that problem. So it might be good for those of you who had this in the spring, go back and reread that section on radiation, 3 or 4 pages. But this is kind of similar. So light does not carry impetus. We could say it analogically carries momentum in the sense, or impetus, in the sense that it can deliver impetus to another body. So the plana has this wave propagating through it, can act on a receiver and push it, give it a force. So light does not have mass. It's not a property of a massive body. It's a property of a plana. So the plana doesn't properly can't be said to have impetus or kinetic energy, but it can be said to have it analogically in the sense that it can deliver those things to a receiver with this kind of relationship. Okay, let's go back to kinetic energy. We had a massive body. What was the definition of kinetic energy? Come on, guys. What's the definition of kinetic energy? Ooh, good day for a pop quiz.
Rate.
Rate of what?
Transport,
Transport of what?
the intensity of the impetus of the body across the distance.
Yeah, I think I know who's talking. I can't see the lips, so I'm not sure, but I think. Okay, thank you. Mr. Salas?
No, Chandler.
Chandler, Aaron Chandler, sorry. These masks are driving me nuts. Where's Mr. Salas? Why do I keep getting you confused with him? I don't know. Okay, sorry. Okay. Remember, we said it's like taking a dump truck with sand or a Ferrari with sand only in the trunk, right? The dump truck carries a huge load, but it goes slow. The rate of transport of the sand is the product of the load and the speed. So the load is the momentum. The speed is always the same for light. So this is like a kinetic energy relation. Dispersion relation is kind of like a kinetic energy. It's weird. In some way that we don't fully understand. Right? So he's going to grow into this and pick out what we can understand from this in chapter 2. Okay. So remember, for a massive body, the speed depended on the impetus. And so instead of the speed of light, which is the same always for any color, back in the plana, in the bare plana, we had this P over M, but there has to be a factor of a half because of this variation. The speed depends on the momentum, on the impetus, so you have to work out what happens if you ramp it up, so you get a factor of a half. It's the calculus. Kinetic energy of a massive body is P squared over 2M. Okay, so there was the wave equation for light. We got something that looks very suggestive. Back to this dispersion relation, these things are connected to each other. What are we going to do for the massive particle, the electron? We want to write a wave equation that has the appropriate dispersion relation. So we have the energy for a free electron is just the kinetic energy. And using the de Broglie relation, we have h bar squared k squared over 2m. This is going to be equal to then some frequency associated with the electron. But what is the meaning of this frequency and what is the meaning of this wave number? Remember that we're talking about the guiding wave structure that always accompanies the electron. So the correct dispersion relation is telling us about how this takes place. The two things, not the details. The net effect is that the guiding wave and the electron are working together and that there's a frequency involved and a wavelength. And so the dispersion relation we're going to be looking for is this. Okay, so we want a wave equation that's going to give this dispersion relation. Okay, how do we get an omega? If we have a solution like the IKX minus omega t, we get an omega.
But time derivative.
Time derivative. One time derivative, not two, just one. And there has to be an I in there. Because when I take the time derivative, minus I omega. I need an I, H bar out here. Which is going to cancel the negative I. And this is like the energy. The H bar omega on the right hand side is the dispersion. Single time.
Oh,
Now, how am I going to get a k squared?
Station derivative.
Yeah, 2. Second derivative. And I'm going to need a negative sign because we're going to have two i's coming. Okay, we're groping in the dark here. Groping, it's not entirely in the dark. We understand some things. What we're trying to do, because we have something involving a guiding wave, particle being influenced by a guiding wave, we have some kind of wave nature that's combined with the existence of the particle. There's two entities, not just one. Well, we're looking for a wave equation. Well, we have now this piece to give us a k squared. So we combine the time derivative and the second spatial derivative. We're going to get this dispersion relation, which is appropriate for an electron, a free electron. Different than this wave equation, which was the equation for light. So we're about to write down the Schrodinger equation. So you'll read that for class on Friday. The next step here is to write a wave equation using these two pieces, which is called the Schrodinger wave equation. And then we need to begin the process of unraveling what it means. What is this thing is going to operate on something, some function, a wave function. What is it? For light, well, it has something to do with the strength of the field, the electric field, and magnetic field, and the wave propagated to the quantum. What does it mean for the electron? So that's what you're going to be studying that in chapter 2. Chapter 2 is a meaty chapter. We're going to spend a lot of time in chapter 2. Any questions? I've gone a little bit over. Sorry about that. So I think you'll have a good time reading chapter 2 right at the beginning. I'm not going to read it all at once. I'm going to chop it up into pieces. So you're going to read the first few pages of chapter 2.